Angle pairs and diagrams. We learned about vertical angles. Remember what vertical angles are? We learned about linear pairs. We learned about angle addition postulate, which would be adjacent angles, right? So we've learned about, and complementary angles, that's an angle pair. They add up to 90, right? Supplementary angles, that's an angle pair. Okay, but we are going to be talking about them in some new relationships here, okay? So, first of all, the definition of a theorem, and we've talked about this before, but a theorem is a statement that can be proven true, like a formal proof can be written to show that it's true. So if you have, an if-then statement and you're like, oh, I think this is true, if you can write like a flowchart proof or a two-column proof and justify every single step, then that idea that you had becomes a theorem. And that's what we're learning here. People have proven these theorems before, and now we're learning them as theorems. So many theorems and postulates, actually, are stated as conditionals, if-then statements. Obviously, if it's a theorem, it's going to be a true conditional. This first theorem, vertical angles theorem, which we've learned already, says that vertical angles are congruent. How could you write that as a conditional? How could you write that as a conditional? Okay, so we would use they, right, because it's always two angles. So if they are vertical angles, then they are congruent. So that theorem can be stated as a conditional, or it doesn't have to be. You could just say vertical angles are congruent. This box gives us things we're already familiar with a little twist. Reflexive property. We talked about reflexive property before, but it was a property of equality. We said like A equals A, 2 equals 2. Same exact thing on both sides of an equal sign. That was reflexive property of equality. Well, it turns out there's a reflexive property of congruence also. And it's just the same exact thing. A is congruent to A. Maybe angle 1 is congruent to angle 1. Same exact thing on both sides of the congruent sign would be the reflexive property. Okay, we also talked about the transitive property of equality, right? If A equals B and B equals C, then A equals C, right? Well, there's a transitive property of congruence. It works with congruence as well. So if A is congruent to B and B is congruent to C, then A is congruent to C. Okay, definition of congruence. We've learned this one already, right? If A is congruent to B, then A equals B, and vice versa. If A equals B, then A is congruent to B. This shows up in proofs when we're trying to turn a congruence into an equals. Okay, so in a proof, we're going to use the vertical angles theorem in this proof, and we're also going to use the transitive property of congruence in this proof. Okay, so start with your given, like always. 1 is congruent to 4. Given. So we can mark that in our diagram, and we're going to talk more specifically today about exactly what that means. But if you're marking things congruent in your diagram, you want to just match the way you mark the two angles. So if 1 is congruent to 4, I could put an arc and an arc. Sometimes you'll see little dashes like this. But you're matching how you're marking them so that it shows that they're congruent. So 1 is congruent to 4. All right. We're trying to prove that 2 is congruent to 3. So somehow we have to link these together with congruences. Are there any congruence relationships you can make in this diagram? Any congruence relationships? Yeah. Are congruent? Why? Okay, so you've thought ahead a little bit, and you're right. The only way for this 1 to be congruent to 3 is if it's 90 degrees, right? So then you're saying they're all 90. True. But we need an actual reason, like a postulate or a theorem, that we can write as our reason to justify a congruent relationship here. In 1 and 2, we don't have a reason, like a postulate or a theorem, to say they're congruent, right? 1 and 2 are what kind of angles? Yeah, so we could have a reason for that, but what would be a different relationship that would have an actual congruence relationship, Abby? Yeah, so if we pick vertical angles here, then we can say they're congruent, right? But you're right, you're kind of like logically thinking ahead here, but vertical angles are congruent. So what would be congruent to what by vertical angles theorem? 1 is congruent to 3, good. And 2 is congruent to 4, yeah. And both of those are going to have the reason vertical angles theorem. Because the vertical angles theorem, like on the top of this page, said vertical angles are congruent. Okay, so now is where we're going to talk about the transitive property. Because if you have a bunch of equals statements or a bunch of congruent statements, you might want to relate things by the transitive property. And remember, we said the transitive property can be more than 3 things. It doesn't have to be A, B, and C. It could be A is congruent to B, and B is congruent to C, and C is congruent to D, and D is congruent to E, and E is congruent to F, right? Then you could say any of those are congruent to each other by the transitive property. Okay? So I like to talk about this transitive bucket. So I'm going to actually draw a little bucket here. And the way this transitive bucket works is when you have a congruent statement or an equal statement, you could put that pair into a bucket together. If they're equal or congruent to each other, they belong in the same bucket. So I'd have my given. 1 is congruent to 4. I'm going to put 1 and 4 in this bucket. Well, then I have my statements that I got from my diagram. 1 is congruent to 3. That means 1 and 3 can go into the same bucket together. Well, when I look at the bucket I've started, 1 is already in there. So can I put 3 in here? Yeah, because 1 and 3 can go in the same bucket. Now I see my other congruent statement. 2 is congruent to 4. That means 2 and 4 belong in the same bucket. I look at the bucket I've started, and 4 is already in it. So can I put 2 in there? Yeah. So when you're done, you look at this bucket, and now any 2 things in that bucket can be stated congruent to each other, or equal if you were doing equals, by the transitive property. So look at what we're trying to prove. We're trying to prove 2 is congruent to 3. Look in our bucket. Can I say 2 is congruent to 3 now? Are 2 and 3 both in my bucket? Yeah, so we can go straight to our conclusion that angle 2 is congruent to angle 3. And that comes from all 3 of these things being in the same bucket. And the reason it's going to be transitive property of congruence. So now instead of POE, we have POC, property of congruence, right? Because it's not a property of equality now. We have all congruent signs in this one. So it's a property of congruence. Okay, so we're going to discover a few more theorems here. These theorems aren't as widely used. They're not going to be as common as linear pair postulate and vertical angles theorem. Those two, I promise you, you will be using them weekly, if not daily, until June. Those will just always be with us. Okay, so we're going to be learning some other theorems that aren't as, common, but are certainly useful. Okay, this one is pretty common. The right angles theorem. And it basically says, if we have two angles that are right angles, what's the measure of each angle? Two angles are right angles. What's each angle going to be? 90 degrees, right? So the measure of each angle is 90. So if both angles are 90, then what can you say about these two angles? How do they relate to each other? They're congruent, yep. So our right angles theorem says if two angles are right angles, then they are congruent. Now that may seem obvious, but it's going to be, if you're writing a proof and you want to use that fact, you need a justifiable reason, right? We always need a reason under our boxes. So our reason is going to be the right angles theorem. Okay, here is another theorem. This one doesn't have a nice catchy name. It's just a theorem without a name. And it says if two angles are congruent and supplementary, then each angle is a blank angle. I think we may have had this as a rack problem the other day, right? If two angles are congruent and supplementary to each other, then what must each angle be? Kaylee? A right angle, right? Right? So if you have two angles that are congruent to each other and supplementary, they have to add up to 180, so each one has to be 90. So they're right angles. Okay, so this is not a theorem, this is actually a definition. It's a very important definition. And this is going to become a new, it's going to kind of open up new doors for types of problems that we can solve and proofs as well. So this is the definition of an angle bisector. An angle bisector divides an angle into two congruent angles. Okay, so in this diagram, ray AY is splitting this angle into two congruent pieces. So it's called the angle bisector. So which angle is it splitting in half? What would you call the name of the angle? Yep. XAZ. Right, so AY is splitting XAZ into two congruent pieces. It's like if there's one slice of pizza left and there's two of you and you both want some. And you take the little knife and you slice it right down the middle. You don't want one person to get a triangle and the other person to get the whole crust, right? So you're going to get it right down the middle. You're basically bisecting that pizza tip angle, right? Cutting it right in half. That's an angle bisector. Again, remember that angles, you got to think about them as the space between the lines, right? Or the rays. It's a fan-like, right? So think of the angle as, maybe I could highlight it, right? This is the angle. Don't think of the angle as the two rays that are drawn, right? AX and AZ. The angle is that shaded yellow, and you're splitting it in half. Okay, so it's the space that you're splitting in half. It's the pizza slice. It's not, cutting a x in half or anything like that, right? It's the whole slice. Okay. So the type of problem that you might get then is something like this. If ray AB bisects angle EAG and EAB is 58 degrees, what is EAG? So this is almost impossible to do unless you draw a diagram. So sometimes they're going to give you a description and you have to draw the diagram yourself. So this is going to be ray AB bisecting, so cutting in half, angle EAG. So let's start by drawing angle EAG. And by the way, when you're drawing a diagram, if it doesn't specifically say it's a right angle or specifically say it's a linear pair, you don't want to draw your diagram as those special angles, unless it says that it's special. This just says it's an angle. So just draw an angle. Angle EAG. And then ray AB is bisecting that. So it's going to look kind of like our diagram up in the definition box. And you're going to draw a ray, start at A, go through B, and continue forever. That's ray AB. Now they're giving us some given information. If the measure of angle EAB is 58 degrees, EAB is 58 degrees, what is the measure of angle EAG? So they're looking for the whole thing. Well, what would you do to get that answer? Yep. Good. So since they're the same, because bisect means we could mark these two congruent, right? The word bisect, whenever you see the word bisect, you should be thinking, aha, I could mark some things congruent here. Bisect is always going to mean that something is cut into two congruent pieces. All right, so they're congruent. Well, if this is 58, this has to be 58. So one way of thinking about this is 2 times the measure of angle EAB equals the measure of angle EAG. That's the way those two angles are related. 2 times the measure of EAB equals the measure of EAG. Well, if the measure of EAB is 58, then we just have to double 58. Oops. Okay. EAG. So when we double 58, we get 116. Does that make sense? Okay, so this is just formalizing how you look at diagrams and sort of read the markings, right? So there's notation that we have in geometry when we're writing out the description of something, like this is the notation for a ray, right? So we learned that. But also in diagrams, there's notation. There's a way of, telling what they're trying to tell you in a diagram. So marking angles congruent in a diagram, sometimes we just mark it with these little arches, okay? But sometimes like I said, they put little like tick marks on them. Let's just skip down here. Look down to this diagram here. You see how it was going to be too confusing for them to have little arches everywhere? So they use these little tick marks. So angle 1 has a single tick mark. So what's congruent to angle 1 in this diagram? 6, right? Because it matches. And then they have a new measure different than angle 1 is angle 2. It has 2 tick marks, but what's going to be congruent to 2? 3, 4, and 5. They're all marked with those double tick marks, so that means that all of those are congruent to each other. You also have probably seen before how they mark segments congruent, right? So here we have well, this is really highlighting the angle congruence, but see how this has 1 tick mark, and this has 2 tick marks, and this has 3 tick marks on the sides. That doesn't have to do with the angles, that has to do with the sides. That's showing you that all 3 of these are different lengths. If they wanted to show you the 2 things had the same length, you know, they would put 2 tick marks and 2 tick marks or whatever. So in this case, this is congruent to this one. So CA would be congruent to FD. Right? Does that make sense? This is all one diagram. Okay, so in these diagrams, let's write some congruent statements. Angle A is congruent to angle what? In this first diagram. C, good. And then you guys write another congruence there for another pair of angles. So what did you write? Yep. Yep. Good. Angle B is congruent to angle D. Good. Okay, in this next diagram, you can just do the angles. Don't worry about the sides. There's actually going to be 3 congruent statements naming angles congruent. So you guys can finish that one. And then we did this one together already. 1 is congruent to 6, and 2 is congruent to 3, but also congruent to 4, and also congruent to 5. Yep. Yep. So what did you get for the diagram 2? A is congruent to, just finish these congruences in diagram 2. So A would be congruent to what? D, right? And B would be congruent to E, right? Because they both have 2 arches. 2 arches matches. And then C is congruent to F. Oh, I know, I sort of did 2 at first, but this is one diagram. Sorry. That makes sense? Okay. So, when you're looking at a diagram, it's very important to never assume anything except, okay, and the only thing you can assume when you look at a diagram is that lines are straight. If it looks like a straight line, then it is a straight line. That is really the only thing you can assume. And that lends itself to other assumptions. So if lines are straight, then angles that look adjacent are adjacent. What does adjacent mean? Next to each other, right? They're stuck together. They have the same vertex. So if they look adjacent, then they are. You can assume that that thing separating them is a straight line and they're adjacent things. You can assume that angles are vertical angles if it looks like it's 2 straight lines intersecting, right? So you don't have to be told these lines are straight lines. You don't have to be told that. You don't have to be told that these are vertical angles. You don't have to be told that. You can tell by what it looks like. If they look like straight lines, then you can tell that they're vertical angles. Similarly, if they look like straight lines intersecting, then you could tell that this angle and this angle form a linear pair. You don't have to be told that. You don't have to be given that. It doesn't have to be marked. You could just tell that from the diagram. Okay, never assume things are congruent. You can conclude things are congruent because they're vertical angles or something like that when you have a justifiable reason, but you can't just assume, oh, well, that angle looks about the same as that one, so I'm just going to call them congruent. Cannot do that, okay? You never assume angles are right angles. Even though they look like they are, you can't assume. You would have to be told. Okay, so what conclusions can we draw from this diagram right here? Give me some conclusions. Yeah. Okay, so you would say, since 3 and 5 are vertical angles, what could you state about them? Okay, so that's a separate statement. 3 and 4 are supplementary. So that's how they're related to each other, right? Because they are called a 3 and 4 are supplementary because they're called a what? Linear pair. So that would be linear pair postulate, right? So there's two things that we just talked about. We talked about what they're called, linear pairs, and then we talked about how they're related. They're supplementary. So let's do the same thing with 3 and 5, right? You told me what they're called. Right. So they're called vertical angles, 3 and 5, but that means that we can state that they're congruent to each other by the vertical angles theorem. What else can we conclude? And you can use markings in this diagram too. What else can we conclude from this diagram? Yeah. They were bisected. Good. So you would say angle 1 is congruent to angle 2 because they are bisected. That's true. Very good. Anything else you can conclude from here? So 3 and 4 are supplementary, but are there any others that are supplementary? I see one more. Yes, it would. Hard to put that into a statement unless we had like letters here, right? We could say if this was ABC, we could say angle ABC is congruent to angle 4, right? We wouldn't want to say, it would be hard to write a congruent statement for that without the letters. If you were going to write in equals, we could do measure of angle 1 plus measure of angle 2 equals measure of angle 4, right? Okay, but let's stick to congruences and supplementary. 3 and 4 are supplementary because they're a linear pair, but I see another linear pair here. See another one? Yep. Yep, angle 4 and angle 5. Okay, so I'm going to let you guys try this, couple of these on your own, and then we'll go over them together before we move on.